Hi everyone, today we're going to review the gas laws. We'll start with Charles's law, which looks at the relationship between the temperature of a gas and the volume that gas takes up. In the experiments you did in class, you directly measured width, but we could observe that as the width of the container increased, the overall volume of the container also increased. So to be more universal and have more applications, we'll talk about volume for the most part here. Okay, so as the temperature increases, the direct effect on the molecules or the particles is that they speed up, right? With an increased heat, they have more energy and they move faster. So we'll say particles or molecules move faster. And they collide with the walls of the container. Because they're moving faster, they have more collisions with the walls of the container. And so those collisions are pushing the walls of the container out, which means that the volume will increase. So faster moving molecules collide with the walls of the container, pushing the walls of the container out, causing an increase in volume. And we would see a positive slope that would look something like that. The exact slope would be different depending on our data set and our axes. So we can describe this relationship with our math words, which is that Charles's law states that volume and temperature are directly proportional. This directly proportional means that as one increases, the other also increases. As one variable increases, so does the other. Okay. Charles's law can be represented with an equation. We have it written here. V1 over T1 equals V2 over T2. V stands for volume, T stands for temperature. And the 1 and the 2 represent the start and the end of our change. So you can think about them as like start and finish, initial and final, beginning and end. I'll use initial and final because we've done that before when we looked at velocity and acceleration. So V1 is our initial volume. V2 is our final volume. T1 is our initial temp. T2 is our final temp. Okay, so you can take a minute to pause and write that down. I'm going to move on. This equation is a little bit different from the fraction equations that we've done before. So in the past, for example, when we've done unit conversions, I'll write that here. We have two fractions that are multiplied together, right? We make our setup like this, and we have multiplication. When we have a setup like that, we multiply across and then we divide down. So let me give you a really quick example. So say we have 5 over 2 times, I don't know, 3 over 6. Okay. Change my color. What I'm going to do is multiply across and then I'm going to divide down. So 5 times 3 is 15, 2 times 6 is 30, right? I multiplied across both. And then I'm going to divide down. 15 divided by 30, I'm going to come out with 0.5 or a half. Okay, so that's what we've been doing, right, with unit conversions. Now we have two fractions equal to each other. This is for our gas laws, well, 2 of our 3 gas laws. We are going to cross multiply. So let's say I have something similar. I have x over 2 equals 3 over 6. I'm going to cross multiply. Probably done this in math class, use the same rules. So 6x equals 3 times 2, then I'll simplify. 6x equals 6. And then I would divide 6 by both sides. And I would come out with x equals 1 as my answer. Okay, so if the fractions are multiplied, multiply across, divide down. If the fractions are equal, then you should cross multiply. So gas laws, cross multiply. Okay, back to our regularly scheduled programming with an example of Charles's law. All right, so here I'm going to take a balloon with a volume of 4 liters and I'm going to put it in an oven. And I would like to know what its new volume will be. I know the temperature of the air is 273 Kelvin, temperature of the oven is 523 Kelvin. Okay, I like to make a hypothesis with these so that I know my answer is in the right ballpark. So here I see the temperature is increasing, right? It's going from 273 to 523. So the temperature is increasing. So I'm going to guess, right? I know temperature and volume are proportional. I'm going to guess the volume will increase. My volume is going to be bigger, or my new volume will be bigger than 0.4 liters. Then I'm going to plug in my variables. 0.4 liters, V2 is a question. T1, beginning temperature 273 Kelvin, final temperature 523 Kelvin. Charles' law, wrote my equation in already. And so now I'm going to fill it in. So V1, T1 equals V2, T2. Volume 1 is 0.4 liters. Temperature 1 is 273 Kelvin. Okay, I'm leaving V2 in there as my variable. You could put X in. I am choosing not to. And then I'm going to cross multiply. So my new line is 0.4 liters times 523 Kelvin equals V2 times 273 Kelvin. Okay, this is a big mass. I know I want to get my variable by itself. So what I'm going to do is divide 273 Kelvin by both sides. And then I know this goes away. I know the Kelvins go away. I'm left with liters for my answer. And then I'm going to plug into my calculator. I'm going to put that up here. Right, come on up here with me. So V2 equals 0.4 times 523 over 273 liters. And then I'm going to take a second to plug that in. All is one thing. Okay. And I come out with V2 equals 0.77. That was supposed to be a 7 liters. And that's my answer. The new volume is 0.77 liters. And I see that my volume increased, so my hypothesis was correct. I did the math right. All right, moving right along. Next up is Boyle's law, which looks at the relationship between volume and pressure. So when I have a sample of gas and I increase the volume, what that means is that my molecules have more space to move. Therefore, because they have more space, they're going to collide with each other less. So they will have fewer collisions. We're thinking about collisions as being the same thing as pressure. So fewer collisions means that pressure decreases. So I have one variable increasing, the other variable decreasing, and I'm going to have a negative slope. Where I have a lot of space, I have a low pressure, and where I have less space, like for example here, we have a higher pressure, right? More collisions. All right, let's put some math language on it. Boyle's law says that volume and pressure are indirectly proportional. This means that as one variable increases, the other decreases, right, which I see with my negative slope. The equation is here, V1 times P1 equals V2 times P2. Nice we don't have fractions, the math will be a little easier. V stands for volume, P stands for pressure. And then 1 and 2 are initial and final, so V1 initial volume, V2 final volume, P1 initial pressure, P2 final pressure. Okay, you can pause if you need more time to write this down. We're going to move on to our example. Okay, here we have a sample of neon, right, like what we might find in a neon light. It has a volume of 6 liters at 101.3 kPa, so at sea level. And we want to know what the new volume will be if the pressure is now 80 kPa. So I see here from 101.3 kPa to 80 kPa, that pressure is decreasing, it's going down. I know they're indirectly proportional, right? One goes down, the other goes up, one goes up, the other goes down. So my guess, my hypothesis is that the volume is going to increase. My new volume is going to be bigger than 6 liters. We'll see if that comes out as being true with the math. Okay, pressure 1, starting pressure 101.3 kPa, ending pressure 80 kPa, V1 6 liters, V2 question mark. My equation's already filled in. So I'm going to start plugging in my variables. Using a dot for the multiplication sign, you can use whatever you like. Okay, trying to get V2 by itself. So what I'm going to do is I'm going to divide everything by 80 kPa. This goes away, kPa goes away, I'm left with liters. So then I'm going to write V2 equals 6 times 101.3 divided by 80 and liters. And I'm going to plug that in my calculator. And my answer is 7.6, rounding. Okay, so the new volume is 7.6 liters, and that is bigger than 6 liters, right? So my hypothesis was correct. I did the math right. All right, last gas law is Gay-Lussac's law, which looks at the relationship between temperature and pressure. So we know that if the temperature is increasing, our molecules move faster, right? Higher temperature, more energy, things move faster. As temperature increases, molecules move faster. This is assuming that our volume is constant, but a controlled variable. So they're moving faster, they're having more collisions, but they're not pushing out the walls to spread out. They're confined in the same space, whatever space they were in before. So as they move faster, they're going to have more collisions. Right? They'll collide with each other and the walls more, which means that pressure will increase. We'll see a positive slope, right? Higher temperatures mean higher pressures. In math language, we know that means directly proportional. So pressure and temperature are directly proportional. If you want to write in again, right, that as one variable increases, the other also increases, you're welcome to. We have that definition of directly proportional back on Charles's law, so you don't have to. Right, we see a lovely fraction equation, P1 over T1 equals P2 over T2. We know that P is pressure, T is temperature, 1 means initial, 2 means final. So P1, initial pressure. P2, final pressure. T1, initial temp. And T2 is final temp. Okay. A note for Gay-Lussac's law that we're going to see in our example is that the temperatures have to be in Kelvin. If we did these problems with the temperature in Celsius, we would have negative numbers, right? The best part of Kelvin is that there are no negative numbers. If we had negative numbers, that would make our whole fraction negative. It would be a whole mess. It would be a mathematical mess, and the proportionalities wouldn't work out. So these equations were designed to be used with only positive numbers and to be used only with Kelvin. So I'm going to show that to you right now. And actually, if you want to go back to Charles's law and you want to write that note in for yourself there too, that would be a good time, right? So temperature, I'm going to put it here, but you can put it wherever you want, must be in Kelvin. Okay. Back to Gay-Lussac's law. Okay, so here I have my variables. A container of gas is initially at 0.5 atm and 25 degrees Celsius. And I want to know, what will the pressure be at 125 degrees Celsius? I am going to do my unit conversion right in the variables. Here we're going to do the variables first, and then we'll do the hypothesis. So P1, 0.5 atm, P2, question mark, T1 is 25 degrees Celsius. To convert to Kelvin, I'm just going to add 273. So then you can do that in your head. You can do it in your calculator. You are going to come out with 298 Kelvin. And then T2, 125 Celsius plus 273 is 398 Kelvin. Okay, so I can see that my temperature is increasing, right? 298 to 398. It's increasing in Celsius too, but we want to be careful. So the temperature is increasing. And I know that this is a proportional relationship. One goes up, the other also goes up. So temperature increases, I predict the pressure will also increase. My new pressure is going to be more than 0.5 ATMs. And now I'm going to show my work. And I'm going to plug in Kelvin. I'm not going to plug in Celsius. So P1 over T1 equals P2 over T2. So 0.5 ATM over 298 Kelvin equals P2 over 398 Kelvin. I have two fractions that are equal to each other, so I'm going to cross multiply, and I'll write my new line, 0.5 ATM times 398 Kelvin equals P2 298 times 298 Kelvin. Okay, I would like to get P2 by itself. So I'm going to divide this over 298 Kelvin divided by 298 Kelvin. And then I'm going to cross out anything that's on the top and the bottom. So this all goes away, the Kelvins go away, and I'm left with ATM, which will be the unit for my answer. Then I'm going to plug in my calculator. I'll show you that work right coming on up here. P2 equals 0.5 times 398 divided by 298, and that is going to be an ATM. All right, I've plugged it in my calculator. You can tell it's real time plugging in my calculator. And I came out with P2 equals 0.67 ATM. So the new pressure is 0.67 ATM. I'm obviously rounding here, whatever decimal point you want to go to is fine, somewhere in the 1 to 3 range. And 0.67 ATMs is bigger than 0.5. My hypothesis was correct. I'm confident I did the math right. Okay, so those were pretty fast. Work through these on your own. Do the solving in the way that makes more sense to you. If you want to simplify sooner, that is fine. I like to plug everything in my calculator all at the end, so I don't have to worry about rounding in the middle, but that's my personal choice. And we'll do some more practice in class.